series a little bit and take a break from learning new derivative rules. So for the rest of this unit, there will be no new derivative rules. We've covered all of them so far. There will be some in the next unit, but we'll get there when we get there. So starting today, we're going to start looking at the graphs of f and f prime and try to make connections between what we see on the graphs and what's happening in the equations for both f and f prime. So take a look at this graph that we see here. Analyzing something like this in terms of where it's increasing and decreasing and where the relative extrema are. This is something that you probably explored a little bit in pre-calculus, but today we're going to look at those intervals of increasing, decreasing, and those relative extrema and make the connection between a graph which has those characteristics and what's going on with the derivative. So take a look at this graph here. It's a pretty simple cubic function. Not that you need to know that, but if we want to kind of break this up into those intervals of increasing and decreasing and look at those relative extrema, we can see that we've got two intervals where we would call the function increasing. In order for a function to be quote unquote increasing, that means that it's got a positive slope. In other words, if you read the graph from left to right, it's going upwards. So you can see that it's increasing there. It's also increasing on this interval here. And in between, where the function's going down from left to right, we would say that that's where it's decreasing. So as far as identifying these intervals, you can use either inequality or set notation. I don't really care, and the AP test graders won't either. But it should look something like this. So f of x is increasing on the intervals negative infinity to, what is that? It looks like about -1. And you can either just list these intervals separately. You can use this union notation. That's not really a big deal. If you use a comma versus the u, either way is fine. But also 3 to infinity. The function's decreasing in between those two intervals between -1 and 3. So it's going up, coming down, going back up again. Now, what we're really curious or should be interested in here is, you've probably already done that where you've analyzed functions like that before. But what does that mean about the derivative of f? So if the slope of a function is positive, meaning the function's increasing, it's going up, what do you think that means about the derivative? Like, what do you think we can say for sure about the derivative if the function is increasing? Let's think about that. So if the function's going up from left to right, and we've got a positive slope, what does that mean about our derivatives? What must be true about the derivative of that graph when the function is increasing? So it's going to be above the x-axis. And what does that generally mean, like, about the function? Yeah, like if it's above the x-axis, it's positive. Yeah, good. So if you've got an increasing piece of your function, that means that the derivative must be positive. Okay, so I'm going to just write that down here. So when f is increasing, f prime is positive. And that should kind of make sense because, after all, like, what is a derivative anyway? It's just the slope, right? So if the slope is positive of a function, then its derivative must be positive. Similarly, if you have a function that has a piece that's decreasing, along that interval, we can say that the derivative must be negative. So if f is decreasing, then f prime, or its derivative, is negative. And this is a biconditional statement that's going to be true. If f is increasing, then the derivative is positive. You can also say if the derivative is positive, then you can conclude that f must be increasing. So you can kind of go both ways there. Now, as far as the relative extrema go, we've got relative maxima and relative minima. These are going to be sort of the local high and low points of the graph, not necessarily the absolute or the global maximum or minimum, but just within a small enough interval. For instance, like the maximum is going to be the highest point on the graph in a small enough interval. So we can see here that we've got a relative or a local maximum at -1 and a relative or local minimum at x equals 3. Now, as far as what you're going to be needing to look for as far as the derivative is concerned, is what's going on with the sign of the derivative as we hit those relative extrema. And notice that this local maximum is a point where the slope changes from being positive to being negative, right? It's going up and then coming back down. And so anytime that happens where you have a derivative that has a positive value followed by a negative value, you're going to have that local maximum. So you're going to have a max when f prime, or the derivative, goes from being positive to negative. If you have that sign change in the derivative, you know there has to be a local max there. And similarly with the minimum, you can see at that minimum, we've got a negative slope followed by a positive slope. And it's going down and then coming back up. And so as far as the derivative goes, if you have a minimum, then f prime is going to go from being negative to positive. So if you're looking at the derivative graphs, a lot of times if you're trying to get information about what's happening on f, you want to be looking along that x-axis, because anytime you've got the graph of f prime crossing over that x-axis, that means that on f, you've got a relative extreme. So this pretty much is what the first derivative test states. Let's zoom in here real quick. I'm not going to read all this, but basically this first derivative test gives you a way to analyze a function f given its derivative. So if we know what the derivative is, then we can find all the intervals of increasing and decreasing, because we can find where that function is either positive or negative, the derivative. And we can find those relative extrema by analyzing when the derivative changes sign. And so that's what pretty much we're going to do today, is go through a couple examples where we're going to analyze the derivative of a function to say what's happening with that function. All right. Any questions so far? All right, so let's kind of put that first derivative test to work here. And really all that means is we're just going to, like I said, find those intervals of increasing, decreasing, and the relative extrema. So should we get all that in there? So first thing, to find all those things, we need to find the derivative, right? And then once we find that derivative, we're going to use that derivative to find what are called critical values. So critical values of f are any points where the derivative is either 0 or undefined. And what makes them critical is these are the only points where the sign of the derivative can change. In other words, if you want to see a change from the derivative from being positive to negative or vice versa, that can only happen at these critical values. So our strategy for finding all the increasing, decreasing intervals and the extrema is basically going to boil down to finding those critical values. In other words, setting the equation equal to 0 and solve it. And then we're going to construct a number line to make what's called a sign chart to basically keep track of when that function is positive or negative. And that's something you probably played with a little bit in pre-calculus, where you're constructing a sign chart and testing values to see where it's positive or negative. And so hopefully this will be a little familiar to you. So first, let's find those critical values. To do that, we need to find the derivative. So we've got this nice little cubic function here. f prime is going to be the derivative of f, and we could just use the power rule to find the derivative of each one of those terms. And so we'll get x squared minus 2x minus 3. We want to set that equation equal to 0. And then solve for x. Now, technically, you might also have a critical value when this function is undefined, but this is a polynomial function, which is never undefined. So you don't really need to consider that. Usually you only need to consider that if you have like a rational function, something with a hole, or maybe a vertical asymptote, like with the tangent graph or something like that. But for any polynomial, you don't need to worry about it because they have a domain of all real numbers. There's nothing is going to make that undefined. So anyway, we can solve this by factoring. And this, what would this be? X minus 3 times x plus 1, which gives us two critical values, one at 3 and one at negative 1. All right, now again, those critical values are going to serve as what are called partitions of the number line that we're about to draw here. So let me zoom this out so you can see both. Let's go ahead and draw a number line. And I'm going to label this number line as f prime because we're looking for the values of f prime here. And on that number line, I'll put negative 1 and 3. Those are our critical values. And now we want to test any number that's in those intervals into the f prime and see whether or not it's positive or negative. Now, in these critical values like negative 1 and 3, these are the only places where the sign can change. So like if I want to know if the function's positive or negative at, say, x equals 0, I could plug in x equals 0. We'll find out if it's positive or negative. And then because it can only change at those partitions, then we know whatever sign we get for that will be the same in the whole interval. So basically what we need to do is pick a representative, just any number in each of the intervals, plug it into the f prime, and see if it's positive or negative. And then we'll start making some conclusions after we do that. So you always want to pick like something that's easy to compute mentally here. We're not going to have a calculator. And so using numbers like 1, 0, 10, whatever's kind of easy to calculate in your head, we want to do that. And I also suggest using this factored form of the function because then it'll be a little bit easier to see if it's going to be positive or negative. Just doing the quick mental arithmetic, I think, will be easier. So let's pick a number like negative 10, to serve as the representative for this leftmost interval over here, and plug it in. If I plug in negative 10 to x here and here, and I don't really care exactly what it equals, I only care about the sign. But if I plug in negative 10, that first binomial, negative 10 minus 3 will be negative 13 specifically, but we only care if it's positive or negative. And then if I plug it in to the second one, that will also be negative, right? Negative 10 plus 1 is negative. So a negative times a negative is a positive, which means in this interval from negative infinity to negative 1, f prime is positive. Okay, meaning the slope of f is positive. F prime is the slope of f. So if f prime is positive, that tells me that in between negative infinity to negative 1, the function f, like the original function, is increasing. It's going up from left to right. Okay, so we're not done with all the intervals. We'll do them all, we'll write them all out at the end, but I just want you to kind of see where this is going. Okay, so we're going to write down these intervals of increasing or decreasing using the derivative. So now let's pick a number in between negative 1 and 3. Okay, a number like 0 is probably the way to go there. Always like using 0 because that's easy to compute. And so if I plug in 0 into these two binomials here, I'm going to get a negative times a positive, which would be negative. So between -1 and 3, f prime is negative, meaning it's below the x-axis, but f, we don't know where it is exactly, but we know it has a negative slope. See, from your perspective, it would be going this way. It's going down from left to right. So that would be an interval where f is decreasing. For that last interval, we just need some number bigger than 3. So you could pick 5 or 10 or 100 or whatever is easy to compute. And so we get a positive times a positive will be positive. All right, so we've broken down this number line with a sign chart. Did y'all use sign charts in pre-cal? Is that something that looks, it should look like a little familiar to you, like this whole process. But now we're just using it in a new context. So we've got some values for f prime here. And so what we want to do is understand how that affects f, or what that means for f, I should say. So when f prime is positive, that means that f has a positive slope, or in other words, it's increasing. So the intervals where f is increasing or maybe I should say f is increasing, just to make this a little clearer. F is increasing on the intervals -infinity to -1 and 3 to infinity. Okay, f is decreasing on just one interval from -1 to 3. Now, on the AP test, generally speaking, they're going to be like, if they give you a question like this, like, where's the function increasing? And you go through all this and you find where it's increasing. Typically, they're going to ask you to justify that answer, like give some sort of a justification. Like, how do you know it's increasing? And yeah, you might have all that work, but that's not really, the number line chart is good, like for you, but for, the AP test readers, what they're really looking for is you to interpret and just basically explain how the derivative's value affects f. So if you're trying to find like a justification for this statement, it should be something along the lines of like f is increasing on those intervals because f prime is positive. So the justification doesn't have to be like a super long statement or anything. It just needs to communicate that you understand that f prime being positive means that f is increasing. And similarly, f is decreasing because f prime is negative. Any questions so far? So that's part of the first derivative test. The other part is dealing with the extrema. So we want to find relative extrema, and we don't have to do any more work. Once you have that sign chart, that's really all you need to be able to answer this question. You just have to know what to look for. And like we said on the front page, if the graph of f is like increasing followed by a segment that's decreasing, you're going to have a local maximum there. And if it's the other way around, where it goes like negative, like a negative slope followed by a positive slope, then you're going to have a local minimum there. So if I look back at that sign chart and I say, okay, well, if this is what's happening with f prime, the graph of f, and I'm not going to like actually sketch it out, but just like the little piece here, if the graph of f is going up and then going down, so it's increasing followed by decreasing, that means at that point right there, at -1, we have a local maximum. So we have a local max, and local, relative, those two words are essentially interchangeable. So you might see either one. I'm going to bounce back and forth between them. But we have a local max at x equals -1. And the reason why we know that to be true is because f prime went from being positive to negative. So it's really about that sign change. Okay. Now, similarly, we can say that f has a local minimum at -3. At -3, we have, and I'm not even really going to connect these because we don't know exactly what's happening with the graph, but we do have a negative slope followed by a positive slope on f. Okay, f prime's graph will look a little different. We'll get to that. We haven't really talked about that yet. But f would have a local minimum at 3. So we have a local minimum at x equals 3. And what tells us that that is true is the fact that f prime went from being negative to positive. So that's what your justification should look like. It's really kind of an easy point to get on the free response section, but it's also one of those things that if you don't justify it correctly, it's an easy point to lose too. Those can be some of the most frustrating. So yeah, any questions? I mean, that really is kind of the first derivatives test in a nutshell here. You guys okay with all that so far? So yeah, we'll just do a couple more examples here. Not a ton. Okay, so here's another one, another polynomial function. So first things first, we need to find our critical values. We'll use the critical values to construct the sign chart. We'll use the derivative to basically fill in that sign chart, and then based on where the derivative is positive or negative, we can answer the rest of the questions. So let's start with that derivative. So f prime would be negative 6x squared plus 6x plus 36. And we're probably going to want to factor this, to make it a little bit easier to find those zeros. This one has a GCF of 6. And just to make the factoring even easier, I think we should, since that leading term is negative, we should probably factor out that negative 6 so that when we factor out the trinomial, that leading term is positive. So let's factor out the negative 6 as like a GCF here. So we've got x squared minus x minus 6. And then set it equal to 0. And I guess we might as well just factor it at this point as well. What would that be? X minus 3 and x plus 2. And so now we can find our critical values. Now, negative 6 obviously can't equal 0, so that factor doesn't produce any critical values. But x could be 3 and x could be negative 2. All right, so before we can really analyze this further, we need to go ahead and construct that sign chart. So anywhere where you have some space here, I'm going to just draw it here. Draw that little number line. Again, this is for f prime. And if you don't label that right now, it's not the end of the world, but I think you should kind of get in the habit of labeling your number lines, especially when we get to the second derivative test. We're going to be looking at what the second derivative can tell us as well. So just to kind of keep your work straight, and as you're reading it, making sure you know what you're looking at, you're going to end up eventually having a number line for f prime and one for f double prime. So just get in the habit of labeling those number lines. So yeah, we'll label negative 2 and 3 as our partitions. And now just start plugging things in. Now just be careful here. As we plug them in, we want to make sure that we take that negative 6 into account. Right? That is a factor, so that is going to negate the sign of whatever we get when we multiply those other two factors. So like if we plug in, say, negative 10, we have a negative times a negative times another negative. So that's 3 negatives. So then on that first interval, f prime will be negative. The graph of f prime will be below the x-axis, while the graph of f will simply have a negative slope. Picking a number in between negative 2 and 3, I'm going to go with 0 here. Big fan of 0. Negative times a negative times a positive would be positive. And then if we pick a number to the right of 3, like say 10, we get a negative times a positive, which is negative. So that tells you, like, it gives you starting to give you an idea of what the graph of f prime should look like. It's negative, meaning below the x-axis, then it passes through the x-axis at -2, going above it, and then kind of comes back. So in other words, like, we don't know exactly what it looks like yet, but the graph is going to do, something like this, right, where it's like below and then above and then below. But the graph of f, which is really what we're focusing on today, is going to have a negative slope. We don't know where it is in relation to the x-axis yet. In fact, we can't know right now. But going down, coming back up, tells us we have a local minimum at -2. And then if we're going up and then coming back down, so something like this, and yeah, these are probably connected. I could probably put this a little lower, but again, we're not really like too worried about what the actual graph looks like. Just kind of getting the idea of what's happening at those critical values and in between. So that gives us pretty much everything we need to answer these questions. F is increasing on just one interval here, -2 to 3. And that's because f prime is positive, and f is decreasing on two intervals, -infinity to -2 and 3 to infinity. And that's happening because f prime is positive. Oh, negative. Let's fix that. There we go. So we kind of already talked about this just briefly, but we have those points now where the relative extrema exist. So we've got one at -2. So we have a local or a relative minimum at x equals -2. And we know that to be true because f prime went from being negative to positive. That justification is almost, well, I think it pretty much is as important as the answer itself, like when they're scoring the test. It's usually like 1 point for the answer, 1 point for the justification. And a relative maximum at x equals 3, because f prime's going from being positive to being negative. Any questions so far? Okay, just I think like 2 more problems here, and then we're done for today. For this first one actually gives you f prime instead of just giving you f, so that's kind of nice. We don't need to find the derivative because it's already given to us. So let's find the critical values, and it's already factored, so just set that equation equal to 0, and you really don't even have to do that much work here because it is already factored. We'll get 3 critical values here, 1 at 3, 1 at -1, and 1 at -7. So now I'm going to construct that number line. Just kind of zoom out a little bit. So here we've got 4 intervals, but the same process. We're going to go through the exact same process here. So plug in a number like -10. Now, this first binomial is squared, so that will never be negative, right? You can't, unless we're dealing with complex numbers, which we are not. We're only dealing with real numbers today, or really the whole year. Anytime you square a real number, it will not be negative. So you don't really need to worry too much about that first binomial. You can just skip that because that's not going to change the sign. And then another thing to keep in mind is if that binomial is cubed or being raised to some odd power, that's not going to change the sign. When you cube a positive number, it remains positive. If you cube a negative number, it remains negative. So as you're doing the mental math, you don't actually have to cube it, okay? Because that's not going to change the sign. We don't really care exactly what the value is at this point. We just care about whether or not it's positive or negative. So you can ignore that. So the only two computations you're doing in your head are really x plus 1 and x plus 7. Nothing else is really going to affect the sign. So if I plug in negative 10, I'm going to get a negative times a negative is a positive. Plugging in something like negative 2 gives me a negative times a positive, which is negative. If I plug in 0, I get a positive times a positive, which is positive. And if I plug in, let's say, 10, I get another positive. So one thing to point out here is, notice how the sign doesn't always change at a critical value, right? That's the only time it can change, but that doesn't mean it absolutely will change. It is possible to have a slope of like 0 in between two positive slopes. Yes, sir.
Can you just do the multiplicity trick though?
That's yes, you can. If you remember that from last year, so what he's asking about, if you didn't hear him, he asked, can you do the multiplicity trick? And yes, if you have a polynomial function, and so that's why I want to caution you, because you might get something that's like e to the x times sine x or something like that, where it would be a little bit harder to tell. But if you've got a polynomial, yes, when you have an even multiplicity like this, what you saw in pre-calculus when you're using this to like sketch out polynomials, you say, oh, when you see that even, that means that the graph's like bouncing off the x-axis, right? And so you should not expect a sign change. And that's going to be true here too. Is if you have one of those binomials squared to the fourth power, you should not expect a sign change. And if it's an odd degree, then you should expect a sign change. Now that's good for polynomials, but again, like not all the functions will be polynomials. But if it is, absolutely, you can still use that trick. And really not so much a trick, but just a sort of an analysis of what's happening. Yeah. Now, as far as like what the graph of f looks like there, you might be thinking like, how does that happen? So this is f prime, but if we're thinking about f at 7, yeah, we've got a local max because we're going from positive to negative, and then we've got a local minimum at negative 1. That's going down and then coming back up. But how would we get like two back-to-back positive slopes with like a slope of 0 at negative or at positive 3? Because the slope is 0 at 3. And so what's probably happening there is something that looks like this, where it's positive, but it gets close to 0, where we have like one point where the tangent line is horizontal. So kind of like that snaking behavior you see in like a cubic function around the origin. And then continues to be positive. So it's like almost looking like it wants to turn the other way, but like last minute, the function kind of forgets its keys in the house and has to turn around and go back in, right? So it's like, okay, I want to turn around, but nope, I'd changed my mind. I'm still going positive. So something like that. Okay, so now we can break down all these answers. So it'd be increasing. F is increasing. On the intervals negative infinity to negative 7. And then for those other two, when you have back-to-back positive intervals like that, you can list them separately if you want, if that makes you more comfortable, but you can also combine them. So it is okay here to say that it's increasing from negative 1 to infinity. And if you're looking at like the graph like this, I think it's kind of clear why that's okay. It's like it's increasing at like no matter what point you pick on that graph, the point to the left of it will have a smaller value, be below it, and the point to the right of it will be above it. Yeah. So yeah, you can combine those. But if you don't combine them, that's okay if you leave them separate. As far as the justification, this is because f prime is positive. And then we have one interval where f is decreasing from -7 and -1, and that's because f prime is negative. We already kind of talked about this a little bit, but didn't write it down. We've got a local maximum at x equals -7 because the slope, or f prime, went from being positive to negative. I'm just trying to fit everything on here. A local minimum at x equals -1 because f prime went from being negative to positive. And even though we have a critical value at 3, just because you have a critical value does not necessarily mean you have a local extreme. It just means that if you have a local extreme, it'll be on there. So like at 3, that's not a maximum or a minimum, so we're just not going to list it. All right, one last question. We've got a multiple choice here from an old AP test. And I don't know if you've noticed this, but like some of these multiple choice questions that I've given you, some of them have 4 answer choices and some of them have 5. And whether or not it's got 4 or 5 can tell you like how old the question is, because they do not give 5 options anymore. The AP test for the past few years has moved away from having 5 multiple choices to just 4. So if you see 5, it's an older question. It's still probably a good question, but if it's got 4, it's a newer question. I don't know if you ever noticed that. But anyway, okay, so it says at the point where x equals 2, what is true about this function? So we need to analyze the derivative at x equals 2 here, okay? Now, before we get into that, let's kind of break down each of these answer choices to see, like, how would we know that that's the answer? So if A was the answer, it says f of x is increasing. The way we're going to know if it's increasing is if the derivative is positive at x equals 2. So in other words, the derivative at 2 must be positive. If that's true, then our answer is going to be A. Similarly, if that derivative is negative, then f will be decreasing. We'll have a relative minimum if at x equals 2, f prime goes from being negative to positive. And similarly, we'll have a maximum if f prime is going from positive to negative. So once we find the derivatives, set it equal to 0, find that critical values if there are any. Or actually, we wouldn't even have to do that. We just need to plug in 2 and see what happens. Then we'll be able to answer this pretty easily. C says, f has a discontinuity. Just as a little reminder here, discontinuities, those are your holes, asymptotes, or jumps. So this, polynomial, exponential functions, both of these have a domain of all real numbers, so we're not really expecting anything like that to happen. All right, so let's find that derivative, f prime. And that first term will just be 6x. The second term, we're going to have to use the chain rule. We got e to the x squared. And the College Board loves that chain rule. It is going to be pretty common from here on out. You kind of expect to see, it's almost kind of a surprise when there is no chain rule. But anyway, derivative of e to the x squared is just going to be e to the x squared times the derivative of x squared, which is 2x. So now let's see what's happening at x equals 2. F prime at 2 will be 6 times 2 plus e to the 2 squared times 2 times 2. We can simplify this just a little bit, but not much. 6 times 2 is 12, plus 2 squared and 2 times 2 are both 4. So I'll just write this as 4e to the 4th. All right, and that's as far as you need to go, because now we have the value where x is 2, and you just need to analyze that number and ask yourself, is it positive or negative, really? It's not 0, so it can't be the relative maximum or minimum. I guess I should have mentioned that. Like, that can only happen at a critical value. So maybe I'd say add a little something here to say that f prime equals 0. F prime of 2 equals 0. So it doesn't equal 0, obviously. So yeah, is that number positive or negative? Positive, yeah. 12 plus 4 times e to the 4th, that's definitely positive. So our answer is A. All right, we will continue working with the first derivative text next time. Okay, just kind of take it a little deeper. And then after that, we'll look at the second derivative test and practice some curve sketching. That's really all we're going to do for the rest of this unit. Is just really focus on the connections between the graphs of f and f prime and f double prime.